Okay, so first of all, we've been talking about redox reactions. You guys have probably already figured out that we learned the 5 reaction types. We learned single replacement and double replacement and combination and decomposition and combustion. We learned all of those. And when we learned how to do redox reactions, aren't redox reactions those still 5 same types? It's just the only difference between a redox reaction is when we have oxidation and reduction occurring, which means our oxidation numbers are changing. But it's still the same basic concept. If it's single replacement, single replacement. Double replacement, double replacement. You just now have to focus on our oxidation numbers, right? So let's look at a few of them. There are 2 types of reduction reactions. There's one that I like to call simple, and then there's another one that is complex. Okay, so the simple ones are easy. So like for instance, this is a simple. What kind of reaction is happening right here? Okay, it's a single displacement, right? Do we see calcium is going to be replacing hydrogen? Hydrogen is going to take the place of calcium. It's a lot easier to see. And you guys know that when we're dealing with water, you can rewrite water as HOH. And it makes it a little bit easier for us to see that calcium is going to be switching places with hydrogen, and hydrogen is going to become over here all by itself, and we see that in the form of our diatomic molecule hydrogen, correct? But it's single displacement, correct? But we're being a little bit more specific, and we're calling it hydrogen displacement because what's being displaced? Hydrogen. But this is a simple redox. We don't have to worry about electrons because if you look at the oxidation numbers, it really doesn't affect us trying to balance our equations. Okay? Yes, our oxidation numbers change because calcium started at 0 and it came over here to 2 positive, but then we had a change in hydrogen too. Hydrogen over here is elemental, so now it's 0, correct? And it started off over here as +1, but there's 2 of them, so that means that it's +2. So if you look, yes, calcium's oxidation number changed. Yes, hydrogen's oxidation number changed, but they changed in the same degree, so do we have to worry about balancing out the charge? No, so we wouldn't have to do electrons and all that fun stuff because it cancels out. So on this side we had a charge of +2, and on this side we had a charge of +2, so overall is our oxidation number changing? No, so this is why this is a simple redox, because our oxidation as a whole did not change. The individual numbers changed, but the reaction as a whole didn't change. So let's look at another type of simple. We have metal displacement. Again, what type of chemical reaction is this? Single displacement. Zinc is coming over here. It's going to displace copper. Copper is going to come over here and be by itself. We have to look up our activity series, right? Zinc is more reactive than copper, so therefore zinc is going to replace copper. So that's why we have over here, which again, let's write out the oxidation numbers just to see what happens. Zinc is elemental form, so it means it has that oxidation number of 2. Over here, zinc is bonded to sulfate, which is 2-, which means zinc has to be. So yes, we lost electrons, we gained an oxidation number, right? So let's see what happens to copper. Copper over here is elemental, so it has an oxidation number of 0. Over here it's bonded to, on the left it's bonded to sulfate, which means it has to have a charge of 2+. So yes, our oxidation numbers change, but as a whole, did our reaction change oxidation-wise? No. So do we have to write electrons and waters and hydroxides and all that stuff? No. You could just balance the equation because everything stays the same. So let's look at another type of simple. We have halogen displacement, right? These are kind of named. They're all, so far, aren't these all single displacement? We're just dealing with different types. What's going to happen to chlorine? Who is he going to replace? Bromine. Chlorine is negative, bromine is negative, so this time around we have to see that chlorine is going to be replacing our halogen, which is bromine. And how do we remember who can replace who? Which is above on the periodic table. So if we're looking at our halogens, chlorine is above bromine, correct? So can chlorine displace bromine?
Yes.
Yes. Can bromine displace chlorine? No. You have to, when we're dealing with halogens, we're dealing with nonmetals, we have to look at where they are on the periodic table. Okay, so Now let's look at our oxidation numbers. Chlorine, this is elemental on the left, so what kind of charge does it have? 0. Over on the right side, chlorine is bonded to potassium, so what kind does it have over here? Bromine on the left is bonded to potassium, so it is. On the right side, it's elemental. So did our oxidation state change? No. So these are called our simple redox. We just balance the equations and we call it a day. Okay. There's actually one more example. This one is not single displacement. It's combustion. Which combustion aren't always simple redox, but if it's a complete combustion, which means we have carbon dioxide and water, it's probably going to be a simple redox. If we don't have carbon dioxide, so maybe it went to carbon monoxide instead, that's probably not going to be a simple redox, so you need to take it one step farther. But let's look at our oxidation numbers again. So, hydrogen, what kind of oxidation number does he have? +1, but there's 4 of them, so altogether we have +4, which means carbon is -4. Oxygen, -2, but there's 2 of them, so -4 altogether. Okay, so this one's going to be -2, -4. Oh, we're not worrying about our coefficients yet. Let's look at the rest of it. We're just looking, so then oxygen's over here, 2 minus, and then we have +2. So honestly, if we kind of look at this like a whole, let's see here, we have -4. So we did have a change here, correct? Hydrogens. If we then look at our coefficient, it'd probably be the same, right? Because our coefficient was up there. If we look at our oxygens, stay the same. So as a whole, is our oxidation changing? Did our oxidation state change as a whole? Well, let's look at our coefficients. This one we haven't had to look at our coefficients so far, have we? Because most of the time we could figure it out without our coefficients. So now let's look at our coefficients and see if it changes anything. So that means that this is actually going to be, on the oxygen on the left side means it's actually going to be -8 because there are 2 of them. So on the right side, if we look at water, it's going to be +4 and -4. So then our carbon changed, our hydrogen didn't, our oxygen looks like it changed, but remember it's in 2 spots, so we have -4, -4, which equals -8. So when we look, this time we had to look at our coefficients, but again, as a whole, no. Okay, so now let's start looking at the hard ones. Let's look at our complex redox. There are 2 types of our complex reduction reactions in which we have to do electrons, hydroxides, waters, and all the fun stuff that we've been doing, right? But now we're going to actually give names to them. So if we look at the first one, it's called a disportionation, and the other one is oxyanions, and I'm probably going to say the first one wrong every single time. So let's look at that one. Basically, in these types of chemical reactions, we have one guy that is both doing oxidation and reduction. The easiest way to pinpoint this type of reaction is if we look, chlorine, he went here, and he went here. He went to 2 spots, correct? So this is kind of a red flag. Oh, this is probably a complex redox reaction because chlorine is going into 2 spots. So I bet if we do the oxidation numbers on chlorine, he's going to both get bigger and get smaller. So let's just go ahead and do them. What is our oxidation number on the left? 0. Okay. When it is bonded to oxygen on the right, oxygen is -2, which means chlorine in this case has to be +1, which kind of goes against the rules we know, but we know, as for one of our rules for oxidation number says, when halogens are bonded to oxygen, they carry a positive charge. That's one of our rules, correct? Are we memorizing those yet? Kind of. Okay, so now let's do what? Well, it has to be negative overall. See the negative charge right here? It's a polyatomic ion. Okay, so now let's look and see what happens to chlorine on this when it's all by itself in the aqueous form on the right. Chlorine goes from 0 to -1, so what's its oxidation number on this side? -1. So this time, do you guys see how chlorine, if we write out our half reactions, we went from Cl to OCl minus. In this half reaction, our charge went from 0 to +1, so we gained, right? Our charge went up, which means it is oxidation. Then chlorine went to Cl minus, and our oxidation went from 0 to -1, which means it went down, so this must be reduction, correct? Okay, so did chlorine do both things? Did it do oxidation and reduction? Yes. How do we, what's the red flag for, oh, this is probably a complex redox reaction? He's in 2 spots. Okay, so let's look at the next one. Okay, whenever you guys see permangate and dichromate, which are some polyatomic ions that I didn't make you memorize in Chemistry 1, but I put them on your cheat sheet this year, and we probably use them enough that you're probably starting to memorize them, right? Okay, whenever you see permangate, which is MnO4 minus, and dichromate, Cr2O7 minus, you should go, oh, crap, this is going to be a hard one. As soon as you see those guys, I mean, that's what I do when I see them. This is going to be a hard one. This is not going to balance easily. We're going to have to do electrons. This is going to take a lot of work. So this, I mean, to me, that sounds complex, right? So as soon as you see MnO4, Cr2O7, you might as well just get out your pencils and your cheat sheets and start writing them out, correct? So I did this one in the notes, I don't know, 2-3 days ago. So you actually have this example in our notes. I actually don't think it's bound. You need to add a coefficient right here. I meant to fix that on yours before I made copies, but I didn't. So go ahead and add that coefficient in really quick. To make this a balance, we balance this equation nice and pretty doing the hard way in notes a few days ago. Okay. So basically right now what I'm trying to teach you is I'm trying to teach you when you're going to some easy ways to skip work, correct? All right, so now let's practice predicting our reactants and predicting our products. If I give you reactants, let's see if we can figure out what their products are going to be. So here are some oxidizers. Here are some reducers. Do you need to memorize this? No. Why? We have a cheat sheet. Okay? If I don't have them memorized, I'm not going to make you guys memorize them, right? So, cheat sheet, you might want to get it out. No. If I don't have them memorized, I'm not going to make you guys memorize them. I don't have them memorized. Sometimes. It depends on the professor. Some of them are mean to make you memorize. Especially when you get to PChem. Physical chemistry. That was fun. Not really. That was horrible.
What was your worst, what was your worst class?
Organic is horrible. Okay. So, if we remember, redox reactions mean that there's a transfer of electrons happening. Sometimes in our simple redox, they balance out so we don't have to worry about them when we're balancing equations, just like I was showing you with the single displacement, right? Sometimes they don't balance out in the complex one, so we have to put them in and we have to set them up in our half reactions and do all of that work, correct? Okay, so oxidation numbers of at least 2 elements must change. Single replacement, some combination, and some decomposition reactions are redox reactions, but not always, because like I said, we have to have a transfer of electrons. If there's no transfer of electrons, then we don't have a redox reaction. That's the whole point of doing redox, is we have to have a transfer of electrons. Okay, so in order to predict the products of a redox reaction, you have to look at the reagents given to see if there's both an oxidizing reagent and a reducing agent. So what is an oxidate? Remember when we were talking about oxidate or oxidizing agent and reducing agents? Those are the ones that are causing oxidation and reduction to happen. So we're going to get practice at identifying them in just a minute. So when you are reading problems, you need to look for words such as acidic or basic. Those are definitely telling you it's redox, and those are also giving you a hint as to what some of your products are meaning. If it doesn't mention if it's acidic or basic, assume acidic. Okay? Remember, there's exceptions to the rules, but those are far and few between. So if you're not given the exception, go by the rule. Does that make sense to everybody? Basic solutions are the exception. So if you're not given basic, assume acidic. All right, so let's look at the first one. We have solid copper is added to dilute nitric acid solution. Ooh. Keyword. What's our keyword? Acid. It's telling us something, right? Okay, it's telling us we are in an acidic solution, and it's not only that, but it's telling you it's nitric acid, and it's telling you that it's been diluted. Okay, so let's look at our cheat sheet. So if we pull up our cheat sheet, and we got to try to figure out what. I lost my cheat sheet. I can get you one in a second. I'll have to make a copy of it. Okay, so if we get out our cheat sheet and we look at it, we can see that. Let's try to find nitric acid. Nitric acid, we're looking for nitrate bonded to hydrogen. Oh, we see HNO3 up here in the important oxidizer, right? Okay, and then we see we have two versions. We have concentrated and we have dilute, correct? And if you look, doesn't it give us two different products? So which one are we dealing with? Dilute. So if you read over, what is going to be formed? NO. So we're going to go from NO3 minus to NO. Oh, why did I put NO3 minus and not HNO3? Anyone? You're way ahead of us. Why did I not write my hydrogen ion? Why did I not write HNO3? For giving us our extra step. We know hydrogen is soluble, correct? So when we are putting this in aqueous, spectator ion, right? And we don't have to worry about those when we're doing our redox reactions, right? Okay, so we have NO3 going to NO, but that's only part of it. We also have copper, right? Copper. Okay, so let's look up copper. Copper, oh no, it's not on here. Darn the luck. Well, luckily for us, copper is elemental on one side because it's a solid, correct? So that means our oxidation number is 0. So whenever you guys are dealing with metals, I just always make them kind of go to the next step. So you guys probably know that copper exists in two forms. Do you remember what forms they exist in? 2 plus, 3 plus. So if we're at 0, what's the next step? 2 plus. And if you remember when you're doing redox reactions, is there always a right answer? No, there are several right answers depending. So if you put copper 3 plus, is that going to be wrong? No, as long as your work shows that if you balance your electrons and you do all of that work. So now we have figured out our half reactions, right? So now what do you think we're going to do? We're going to do oxidation numbers. So copper is 0 on the left, and it is plus 2 on the right. That work's already done for us, correct? So now we have to figure out nitrogen. So on the left side, he is bonded to 3 oxygens, which gives us a -6, right? But it has to overall be -1, so it makes nitrogen plus 5. On the right side, NO, what kind of charge does nitrogen have? 2 plus. So nitrogen, our charge went down, which is signaling reduction, not redox. Okay, copper went from 0 to 2 plus, so our charge went up, which means it's signaling oxidation. So here's the question for you. Who is our reducing agent? The copper. Who is our oxidizing agent? Nitrate. Do you see how they're opposite? Copper is undergoing oxidation, which means he is causing reduction. Nitrate is going under reduction, which means he is causing oxidation. Kind of backwards thinking, but when you're trying to identify the agents, it's almost like the opposite. So, do you guys want me to balance this one, or you want me to move on to the next one? Move on? Okay, so let's look at the next one. We have ethanol has completely burned into air, but we don't know, we haven't done organic. We don't know what ethanol is, so I'm going to tell you what ethanol is. Ethanol is C2H5OH. That's what ethanol is. Okay, ethanol has completely burned in air. Woo, woo. Keyword, where's our keyword? Burned. There's a signal word with burn. Completely burned, so it's probably going to be combustion complete, correct? So we take this, air, complete combustion, air, what are we really honestly talking about? O2, and I'm just going to go ahead and write out this chemical reaction. It'll help us see something. Then we're going to have CO2 plus water, and we got all of this information by two words, completely burned. Completely, complete, burned, combustion, complete combustion, right? Uh-oh, what is this? Simple. This is a simple redox reaction because it's a complete combustion reaction, so do we have to worry about oxidation numbers? Nope, so we move on, correct? We can balance it, so let's just balance it really quick. We have 2 carbons on the left, 1 on the right. How do I fix that? Need a coefficient of 2 right there. So that fixed our carbons, but nothing else. So, do you guys want to do hydrogen or oxygen next? Okay, we have 6 hydrogens on the left. We have 4 on the right. So now we have 4 oxygens right here. We have 3 right here. 4 plus 3 is 7. So we need 7 on this side. Right now we only have 3. So if I put a 3 right here, that gives me 6 here, 1 here, 7 altogether, right? We don't have to worry about anything else because it's a simple redox. We don't have to worry about electrons. 5. Okay, so let's look at the next one. Okay, we have sodium metal. Sodium is Na. We know this is a solid, so it has an oxidation number of 0. Sodium metal is added to water. We can rewrite water as HOH. Ooh, red flag. What kind of single displacement? Hydrogen displacement. We can go ahead and finish writing it out if we wanted to. Sodium and hydrogen switch places, so we're going to have sodium hydroxide plus H2 because it's a diatomic molecule, right? So hydrogen displacement, is everything balanced? No. Why is everything not balanced? We had to add a diatomic molecule, so easy to fix. Put a 2 right there, put a 2 right there, put a 2 right there. Do we have to worry about electrons and waters and hydroxides and all that fun stuff? No, because this is simple redox, correct? All right, so let's look at the next one. Number 4, we have hydrogen peroxide. Ooh. Red flag, peroxide, uh-oh. This is probably going to be a hard one. We have a red flag right off the bat. As soon as I start seeing red flags, it starts making me want to go, ugh, work, right? So hydrogen peroxide is added to a solution of iron 2 sulfate. So what I'm going to do is I'm deciding, as soon as I saw that red flag, it's telling me I'm going to have a complex redox. Let's just go ahead and do our reaction. So we're going to have hydrogen peroxide, which is H2O2. It is added to a solution of iron sulfate. Someone else see a red flag right there? Iron sulfate. What do we know about sulfate? It's aqueous. So let's not even worry about it. Okay, iron 2, Fe 2 plus. And remember I said, just kind of go to the next step. Iron exists in multiple forms, so what's one more step up from iron 2 plus? Iron 3 plus. Okay, so now we need to, how do you think I'm going to figure out my other half reaction for hydrogen peroxide? Cheat sheet. Okay, hydrogen peroxide, if we look, it's in both spots. It's an important oxidizer and it's an important reducer. How do I know which one I'm going to do? We have to figure out what iron's doing because hydrogen peroxide's got to be the opposite, right? So our charge went up, which means that this one is oxidation. So that means that H2O2 has to undergo reduction, which means it is an oxidizer. So H2O2 is going to go to H2O, water. Does everyone see how I looked those two things up? Okay, so do you guys want me to go ahead and balance this, or are we pretty comfortable with balancing redox equations? Or do you want me to go ahead and do this one? Do this one? Okay, so this is a peroxide, so that means oxygen is 1 minus, not 2 minus, correct? So if oxygen is 1 minus, that means hydrogen has to be 1 plus. So then over here, oxygen is going to be 2 minus, and hydrogen is going to be 1 plus. Okay, so down here, iron went from 2 plus to 3 plus. So we don't have anything to worry about, correct? Except now we need to balance. We don't have to do any oxidation numbers. So let's balance the top. Our hydrogens are balanced, our oxygens are not. How do I balance oxygen? Add water on the right side. But then that messes up our hydrogen, so we have to add 2 hydrogens on the left. So now let's balance the bottom one. Iron's balanced. We don't have to worry about oxygen. We don't have to worry about hydrogen. So next we have to move on to our electrons. Now, this is a tough one. Yes, oxygen has a -1 charge on the left. Yes, oxygen has a -2 charge on the right. But each oxygen gained, right? Each oxygen gained. Because we have H2O plus H2O, so technically we have 2 H2Os, correct? But we have 2 oxygens, so they went from -1 to -2. So did we gain 1 electron or did we gain 2? We gained 2 electrons. Did I lose anybody there? Because each oxygen gained an electron, each one. So then to balance out our electrons, we're going to add 2 electrons, not 1, because each oxygen gained 1. Okay, iron on the bottom. We lost an electron and go into infinity, correct? So we have to add 1 electron on the left. So now what do? I have 2 multiply by 2. Well, multiply who by 2? Multiply this guy by 2, which is going to change my coefficients to 2, 2, and 2. Now what do? Cross out everything that we have in common. Okay. Now I can simplify and write my equation, right? So, or we'll do black actually this time. So I'm going to have 2 hydrogens plus H2O2 plus 2 Fe2 plus yielding 2 H2Os. Why did I write 2 H2O? We have 1 here, we have 1 here. Put them together, right? Plus 2 Fe3 plus. Starting to get the hang of this? Okay. So, I want you guys to try the next one on your own. I want you to try number 5 on your own for just a second. Right off the bat, you should see a red flag. You should know what you have to do. You don't have to balance it if you don't want to, but I do want you to write your half reactions, okay?